Now we're going to talk about probability, but first we need to introduce some definitions. So a random experiment is a process whose outcome is uncertain due to randomness. The specific outcome that we get from the experiment is an observation. So let's say that our experiment is to flip a coin twice. The observation we get might be heads followed by tails. So our experiment is flipping the coin. The observation is what actual results we got, right? What outcomes. In this case, heads followed by tails. The sample space is a set of all possible outcomes of an experiment. And most authors will write it either as capital S or the Greek character capital omega. So here we might be having the experiment. Once again, is flip the coin twice. And then the sample space that we might choose would be this. We could get heads followed by heads, heads followed by tails, tails followed by heads, and tails followed by tails. Now, one thing to note, though, is that sample spaces are not really unique. You may look at this and think, well, yeah, that's obviously what you would write. And this probably would be what I would use, but they're not unique. So let's say, for example, we were choosing a card from a deck of 52 cards, right? One sample space would be, say we get, okay, the ace of spades, the two of spades, the three of spades, and so forth, for a total of the 52 cards, right? So it'd be 52 different possible outcomes. But another sample space we could use would be, we get a spade, a diamond, a club, and a heart. Right? Those are the four suits that we have. So this could be my sample space. Now I probably would choose this instead of this for this reason. Because we have a lot more granularity here, I can answer more questions about this. If I were to ask, without going into the definition yet of probabilities, what is the probability of drawing a spade if I were to choose one card from the deck, I can answer that with either of these two sample spaces. But if I were to ask, what is the probability of drawing a jack of diamonds, I cannot answer that with this question because I don't differentiate between the different cards within a suit. Here I can. So this particular sample space gives me more flexibility to answer questions. And this would be the one that most people, I think, would choose. All right, but either of those would be possible, and there'd be others as well. You know, going back to the first one here, you might have a sample space consisting of flipping a coin twice, and you get a heads on the first flip, or you get a tails on the first flip, right? That'd be two different possibilities. Now, ultimately, what we care about are events. And I just gave you some events, actually, when I said something about we flip a coin twice and, we get heads on the first flip. That might be a possible event. But what events are subsets of the sample space or collections of sample points, those that match a certain thing. So let's say our experiment is to roll a six-sided die. Right? What's our sample space? Well, I might choose to use what I think most people would be, which would be, say, you could get a 1, a 2, a 3, a 4, a 5, or a 6. That seems like the most reasonable and most obvious sample space, but we could choose others, right? So what events might we use with this? We might have event 1 might be roll a 4. And in terms of subsets, that would just consist of the 4. Event 2 might be real and even value. And what that would consist of would be the 2, the 4, and the 6. So anything that I roll that matches one of these values, obviously it can't match all three, but any one of these would satisfy this event. And then you might even have a third event. Might be roll an even value less than 2. So what does this match? Well, this would be the empty set or the null set, because there are no even values less than 2. The only value less than 2 is 1, and that's odd. But it is possible to not have any elements there, and this would then lead to a probability of 0. Okay? So that then leads right into our next definition. The probability of an event is a real number between 0 and 1, inclusive, which means it could be 0, it could be 1, or any real number in between that represents how likely that event is to occur. Now, when the sample space is finite, so sample space is finite or countably infinite, then we say that we have a discrete probability model. So you have continuous probability and discrete probability, and we're only going to discuss this type. Things where, in fact, we'll only deal with finite, where I can enumerate the possibilities relatively easily. Okay? So how do we come up with these numbers between 0 and 1? There's different ways to do that, but for the examples we'll be able to use what's called the relative frequency approach. And so what that means is the probability of some event will be equal to number of outcomes in the event divided by number of outcomes in sample space. Okay? So what might be some examples of that? So let's say that, for this example, our experiment is to flip a coin twice. Okay? And let's say we have the event to, the first event here will be second toss is heads. And event 2 is first toss is tails and second toss is heads. So what are the probabilities of each of these? They may look at this and think, well, aren't they the same? Second toss is heads, second toss is heads. But they're not. We're going to assume a fair coin. And for this, we'll say the sample space is heads, 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 tails, tails, heads, and tails, tails. And so what do we get for event 1? Well, event 1 is what? Second toss is heads. There's one. There's another one. So this is the size. If you've seen my video on set theory, then you should know about cardinality. And the vertical bars here are saying count the size of the set. So this would be 2 divided by 4. We assume these have equal odds. We're not talking about probability distribution, so we'll just say that likelihood, that likelihood, that likelihood, that likelihood are all equal. So the 2 of the 4 of these will be 1/2, or we say there's 50% probability. In the second case, though, we narrowed things down a little more. We said the first toss had to be tails. And so what was that? Well, tails heads. So that's the only event that matches the second, or the only outcome, that matches the second event. So that's 1/4, or 25% probability. And hopefully that makes sense to you, looking at that example. None of these examples are revolutionary. You know, it's standard to see examples with coins, or cards, or a die, or marbles you choose out of an urn, or something like that. And one reason for doing that myself is that you already have some idea of what these things mean, right? So you're not trying to wrap your head around what we're even talking about on that. Let's look at another example. Let's say the experiment is to roll a 6-sided die twice. So why do I say roll a 6-sided die twice instead of just saying roll a pair of dice? Well, I'm trying to make it more obvious that we have a first value followed by a second value. Because if I were to say just roll the pair of dice and get their values, you might miscount what we're dealing with because you're not differentiating between die 1 and die 2, but we need to get the correct values. So let's say that our events are row 1 equals a 2, row 2 equals a 4, and event 2 would be sum of the rolls equal, and that's 2 words, is equal to 5. So what's our sample space here? Well, one way to look at it would be the tree. So we could roll a 1, followed by a 1, or a 2, or a 3, or down to 6. Or you could roll a 2, followed by a 1, a 2, a 3, or so forth, all the way down to 6 for the first roll, or 6 possible values for the first roll, 6 possible values for each of the second rows, for a total of 36 different pairs, right? These are permutations. And so I'd say my sample space would be a 1 and a 1, a 1 and a 2, a 1 and a 3, ... down to a 6 followed by a 6. So there's 36 different pairs of values here, right? So we're finding the probability of E1. Roll a 1, or on the first row is a 2 followed by a 4. So this is what is the size of this set versus the size of S, which we already said is 6 times 6, which is 36. So there's only one thing in this set, so it's 1/36. That's our probability of getting this. But what about probability of event 2? What is the set that corresponds to this event? Sum of the rolls is 5. So I could have a 1 followed by a 4, a 2 followed by a 3, a 3 followed by a 2, or a 4 followed by a 1, divided by the size of S. And this hopefully makes it a little more clear why I wasn't saying roll just a pair of dice, even though the values would be the same. See, here we can see a 1-4 and a 4-1 look like the same thing if I'm not paying attention to which die is which. But they're really two different things if I think of there being a die 1 and a die 2, right? So now we have 4 out of 36, which is 1/9. That would be the probability here. So there's sort of the basics of this. We'll pick up on some more complicated examples in my next video.